No. There we go. So I've done this in editors quite a few times. You know, I want to type out the numbers, you know, all the d-digit numbers, and the loop invariant, and I want to write macros to do it. So for example, a lot of people, and so that there are two issues when you're looking at your test is how well do you demonstrate these steps, right? And that for me is the biggest thing. And then the next thing is, well, how much did you get the details of the program, of the problem at hand? And so what are the details of this problem at hand? Is, well, you don't have a variable j, right? There are no variables. So if you say do something with the variable j, well, you don't have a variable j, and you can't increment the variable j, right? So where do you get that? That's if you need to grab a 6, you get it from here, and you move the cursor along, right? And so now you want to you copy these down here, and you replace all the pound signs with pound 6, right? So you get the 6 from here, and you grab this and you replace all the pound with pound 6 and you paste it here, right? And that maintains this loop invariant while making progress, right? Because the progress is well, we have them these are all the, you have I digits, and here we have I plus 1 digits, and we have the first up to 5, and so then we have to get up to 6 in one step, right? And then what would the precondition be? Well, if j is 0, then this is empty, right? So the precondition of the inner loop says, well, we have this, and we have the first I numbers, right? You know, we have all the numbers with I digits in them, right? And this is empty, right? So that's the precondition, and the postcondition is. I like to think of you can have different postconditions, but the postcondition I like is this is still empty, but we have I plus 1 digits here. Right? So how do you establish the precondition? Given the precondition, how do you get the loop invariant? Well, the precondition says this is empty, but that's what the loop invariant, you know, when you haven't gone around any times, then that's what this is supposed to be. It's supposed to be empty. Right, and then we talked about how to maintain the loop invariant, how to get the postcondition. Well, the x condition is that you've gone around 10 times. So the cursor is moved down to past the 9, and this is the same as it always has been. But now you have all the I plus 1 digits here, right? And so, and now how do you get the postcondition? The postcondition says that you have the I plus 1 here. So you just take them from here and you put them over here. And you make this empty. Right? So that gives you the postcondition. Right? That's the inner loop. And then the outer loop, the loop invariant will be that you have all the digits with I digits in it, all the integers with I digits. And how do you maintain that? Right? How do you maintain that? Well, you run the inner loop, right? And this is how you maintain it while making progress. So you go from I to I plus 1 to I plus 2. It's just like grading sort. You get more and more digits here. And the precondition, right, is that all of this stuff is empty. So to establish the loop invariant the first time, well, you have to set up this stuff. And a few people got this. If I is 0, that means we haven't gone around at all. You have all the integers with 0 digits here. What's contained in this file? A pound sign, right? In fact, after you have 10 to the I lines after you've gone around I times. So if I is 0, then you have 10 to the 0, which equals 1. We have one line, and it's the pound sign. Right? So that's how you establish the loop invariant, how you maintain the loop invariant. And then the post condition is that you have the answer in main. So the X condition says that when you've gone around this d times, then the loop invariant says that we have all the integers with d digits here, and then you just copy them into main and you're done. Right? People kind of following that? But the real thing is, you guys, I want to get a better sense that you understand this stuff. Right? The details of this. My sense in life is that as people follow these steps, why do I hound people to do this? It's not like people got the right algorithm here. Right? So my feeling is if you really kind of think about the steps, then the algorithm, it's easier to see what the algorithm should be. In terms of running time, maybe it's kind of hard to read here, but a lot of people didn't understand the difference between these two questions. The one is supposed to be, what work does the computer actually have to do, right? And if the output has 10 to the d lines, and each line has d characters, and somebody typed those in. It wasn't me, so the computer must have typed them in, right? So this is the computer time, right? It's the computer time, and then how much work did I personally do? Well, I just cut every inner loop. I cut and paste. So that's a constant amount of work, and I do the inner loop 10 times, and I do the outer loop d times, right? So this is how much work I do, right? And then if I turn it into a macro, then it takes me this much time to set up the macros. And now nobody got this part, but I do have to run the macro, right? And how do I run the macro? I have to tell the computer that it's supposed to increment it d times. And so that takes, I have to do this much time to tell the computer that it's supposed to increment it d times. Right? I have to type in d. All right, so that's all. Oh, and then if you do it, this base b, then this changes to this, and this one actually changes to this because you have to type in the first b characters, right? So that's pretty good. So are we done? Most people got this one. A lot of people got this one. A lot of people got this. Nobody got this so far. But I've only marked 15. But you know what very few people have done? Very few people have noted that the size of the input is log d. Right? Because I set up here, the input consists of the single integer d. Right? So the size of the input is log d. So d equals 2 to the n. So this isn't actually a 10, this is actually a 10 to the 2 to the d. Oh, it's not to the d, to the n. 10 to the 2 to the n. Right? And this one here is 2 to the n. And this one here is n. Right? It makes sense that this, very few things take less than n time because you have to look at the input. So I don't want to make everybody as miserable as I am, but that's the situation. All right. So what are we going to do now? Well, I'm going to painfully continue to mark these, even though I really hate it. I hate it. You know, I pull out a pile of pen and I say, okay, Jeff, mark 10 before you get up off this couch. And then I mark 2 and I go find something else to do. So that's what I've been doing. All right, so what do we want to do in the future is you know, it's good that we've kind of established this relationship now. The relationship is you listen to my steps or I'll fail you, right? And when I started teaching many years ago, people would say, well, why do we have to do it your way? And I would, you know, being liberal myself, I would feel like a dictator and think it was bad to make you do it my way. But, you know, my experience is the chances of the chances of you doing it a way that I want you to do that's still right, it's so small if you don't do it my way that I'm just going to make you do it my way. That's all there is to it. I'm the dictator and you're going to do it my way. Everybody get that? So we're going to do fine in the future because you're going to now know that I'm serious and you have to do it my way. All right? So focus on what the steps are. Know the steps. Know that when you're writing a test, for me at least, what I want more than anything is for you to convince me that you understand the steps. Right? And that the details of the algorithm, you know, they're fun, but they're less crucial than do you understand the steps. All right? So if you got 0 on this test, then your mark has just gone down by 2%, I believe. So the whole thing's worth 7, or 11, and oh right, it was. So if you got 50, there was a 2% somewhere. If you got 50%, then your mark went down 2%. If you got 0, it went down 4%. All right, but you know, I have been known to give people 110 on exams. So, you know, life, you still can get perfect. Any thoughts?
How much part C works out of
I wrote a list of what always happens is follows. I start off with a list of things that I want to see on the paper. And in this case, I came up with 21 things that I wanted to see on the paper. And so I made them worth 5 marks each. So if you got them all, then you got 105. And then I go through and I realize that most people haven't given me any of the things that I want on my list. And so then it starts becoming a little bit more hand-wavy what numbers I put down, right? So in this case, this was 5 marks, and this was 5 marks, and this was 5 marks. But actually, I gave it to you since it's constant. And then if you converted everything based on size, that was another 5 marks. And you know, 5 marks. If 5 marks, those things that were written down here, if you wrote down those, you got at least 5 marks each. But usually it kind of, simply because you wrote them down, I rounded things up. All right, any other thoughts?
So if you say steps, for example, maintenance, you have to show, you say loop invariant, prime, and closed loop, and not active condition is equal to
Loop invariant.
Double prime, or you can just say maintain loop invariant?
I would say that if you really gave a good answer and all you said was maintain loop invariant, then I would give you full marks for it. But if there's any danger that you're not giving me the right kind of answer, you know, write the full thing down. Right? It doesn't hurt you to memorize what I say are the steps and to write them down. Right? So if you said maintain loop, I mean, what should you do in there? You should say, oh, I know the loop invariant's true, so what's the loop invariant? right? I know that I haven't exited. Well, that's not a big deal. I know I did this code, right? So then that gives me that the loop invariant's true, right? That's what's required in this step. And if you did that in the steps and your title was maintain loop invariant, then that was good. But you probably didn't do that, right? So you better at least write the title correctly. Does that?
Yeah.
Everybody good? And really, it feels like we're being harsh here early in the go. But really the reason I'm doing it is I had 10 years of wanting to fail a third of you. And I just don't want to do that anymore. So instead of being nice all along and then having a nervous breakdown at exam time, my goal now is to be nasty as I possibly can early in the game. All right? All right, so we are now...
I have one question, sir.
Yeah.
If this was supposed to be done in 30 minutes,
Yeah.
and you give us 2 hours,
Yeah.
and the exam is supposed to be done in 3 hours, should you
Yeah.
bring a picnic basket? Or
Well,
how does that work?
yeah, that's a good question. It is a good question. And I think I've stayed here for 5 hours. I'm not sure I've ever been willing to stay here longer than 5 hours. But, I can tell you what's going to be on the exam right now. Right? There will be one question very much like this for each unit. Right? Plus, there'll be, a number of those little math questions. And yes, you have to do them. Right?
And there are 5 units?
And there are 5 units.
So 5 questions.
5 questions. And this is kind of par for the course. Right? And just to let you know, in case you're not panicked enough, this is the easiest unit. Right? They get progressively harder. Right? They really do. Right? Well, actually, certainly the last 2 are killers. Right? The greedy algorithms and the dynamic programming. People just, I don't know. If you follow the steps, if you memorize and follow my steps, they really aren't hard. But people just are unwilling to do that. So, do it. Right? Any other questions? So, we were doing recursion. And specifically, we're looking at recursion on binary trees. And as somebody pointed out, recursion comes up a lot in life. I don't know, in my life, I don't know, maybe it doesn't come up as we said, if you're a banker, it doesn't come up, right? But one application of recursion is when the structure that you're working on is recursive. And when I'm trying to come up every year with the new question, let me tell you another thing that makes my life hard. You might not have sympathy for me, but it's hard coming up with these questions. It really is hard. And I feel I have to come up with new ones every year because they're out there, right? Previous ones are out there. And I'm doing something new this year, and I don't know if it's going to help me at all. But I'm not posting the solutions. My thinking is not to post solutions anymore. Right? Because once they're out there electronically, then they're kind of out there forever. And my hope is if I hand you a piece of paper, then 5 years from now I can reuse this question without too much danger that half the class has it. Right? But I was telling this to Carrie, who was an engineer at U of T, and she says if you go across to the photocopy store across the street from the engineering building, they have the photocopy store has a file cabinet with all assignments and tests dating back decades, and they will sell them to you. So, it might be a hopeless case. All right, so trees have this recursive structure. And the way it has a recursive structure is I'm going to say what a binary tree is. It's either the empty tree, or it has a node with a left subtree and a right subtree. Right? That's what a binary tree is. So as I said, you know what? The whole thing's a tree because this thing there is a tree because it's a node and a left and a right, and that's a tree because it's a node and a left and a right, and that's a tree because it's an empty tree. Right? And when we're trying to, right, so let me just say again, if you didn't catch that I was saying this, I'm not sure it's going to be true this time, but at least half the questions that have ever been on tests have been about binary trees. It's hard to come up with questions, and quite frankly, the only reason I'm not doing as many binary trees lately is I think I've asked every question you could ever ask about a binary tree. Right? I mean, I've been doing this 12 years. You run out of questions about binary trees. But if you had a question on a binary tree, then the way you think about it is I'm given an instance, and my instance is the entire tree, but I'm too lazy to look at the entire tree. Right? I personally am only going to look at the root. And I'm going to get a left friend to look at the left subtree and a right friend to look at the right subtree. Right? And how does the communication go? Only thing that the left friend knows is the information I send him. Right? Only thing the right friend knows is what I send him. And how do I send things? By the inputs. Right? And then only thing I know is the root and what they answer back. Right? So, seriously, that is what I just said there. If you just could memorize what I just said there, and the question on the test was a binary tree, that would give it to you pretty well. Right? So if we wanted the number of nodes, then you ask your left friend how many nodes. He says 6, he says 5, left plus right plus 1, right? It's the number of nodes. What's the base case? Is that the base case? All right, good, good. No, because if that was the base case, we haven't solved this problem yet, right? Because you can't go left. So the base case should be the empty tree, and how many nodes in the empty tree? 0. Now, I tend not to be a big reader. That's why I wrote my own textbook. But a lot of textbooks tend to not have the base case be the empty tree. They want to have the base case be a single node, and then you need a lot more cases. Right? If you have the base case be a node, then you have to consider the case where you don't have a left subtree. You have to consider the case where you don't have a right subtree. So do we need this as a base case anymore?
No.
No, because this is 0 plus 0 plus 1 gives the right answer. Right? Everybody get that? So, yeah, that's what I just said. Most programmers don't use it. Base case, empty tree is a fine tree. So here's the code. I'm given a tree. The precondition is I have a binary tree. It returns the number of nodes. If the tree is empty, then the result is 0. Otherwise, I ask my left friend for here's left subtree. I ask how many nodes are in the left subtree, how many nodes are in the right subtree, and I add 1, and that's my answer. Right, everybody see how easy this program is? And in this case, at least, you would admit that if you had to write an iterative program to do this, it would be a lot harder. Right? You'd have to go down the tree and up the tree, and it would be a nightmare. All right, so when you're testing, and this I want to see you do this on tests. This is not another step, is when you're testing to make sure your program works, this is how you should do it. You should think, oh, suppose I had I'm a generic tree with a big left tree and a big right tree, do I have the right answer? Right? And in this case, this number of nodes here plus the number of nodes here plus 1, we're good. Right? What happens in this case when I have a big left tree but not an empty, right? Right, so that case, this case here, do we have to write new code for it? No, because the same code gives us the answer. And you'll note, the way I do it is I write the code for this first. And then I check to see if the same code here works. And I haven't written the code for the empty tree, but I know the answer for the empty tree. Right? I know the answer is 0, so it seems to give me the right answer. Then it's good to test on this one, because this one's sometimes weird. Right? But in this case, does it give us the right answer? Yeah. And this we hardwire in, so we're good. Right? Running time, well, it's the amount of time the left friend took plus the amount of time the right friend took plus I spent a constant amount of work. Right? And it's kind of hard to see if you ran this program and did the stack frames, right? The stack frames would completely mirror the tree. And there'd be a stacked frame for every node in the tree. That's not completely true. They would also be the stacked frames for the empty trees hanging off the bottom. Right? And anyway, it's all constant time. Right? All right, now if we wanted to, all the nodes have data, we want to take the sum of all these data items. How do we do it? We first ask the left friend for what? The sum. We ask the right subtree for the sum. And what's our answer?
Sum plus root.
This answer plus this answer plus the 3. Right? Base cases. All right. What's the base case?
Empty.
And what's the base case's answer?
0.
0. All right. So here's the algorithm. If the subtree is 0, otherwise it's the sum on the left plus the sum on the right plus the data at the root. And we test all these cases, and we're pretty good. All right. All right. What happens if we're doing the maximum node in this tree? Right? There's no order to the nodes. We want the maximum. What do? We get the maximum over here. We get the maximum over here. And our answer is the maximum of those 3 numbers. Right? It's the maximum of the left and the right and the root. All right, so now, this is the hard one. What's the answer for the empty tree? Infinitely small. Anybody think infinitely small is a reasonable answer? Base case. Well, if we're doing sum, we have the sum so far is 17. What's the sum of the empty list?
0.
It's 0. Why? Because our algorithm is take the sum so far and add the new number to get the new sum so far. Right? So we want to take the sum so far and add the first number to get the new number. So the sum so far better be 0. Right? Does that make sense? Yeah, that's what I said. We want to take the old sum plus the first number to give us the sum when we're starting off. What happens if we're doing product? What's the product of 0 numbers? 1. 1, exactly. And if we're doing true, false, if we're doing ands, then the answer so far is true, right? You want to start off things being true, because once they go false, they're never going to go true again. Right? And if we're doing max, then we want negative infinity, right? Why? Is because we start off with negative infinity and we take the first element and we're going to get the first element. Right? Does that make sense? And if we were doing min, then we do plus infinity. Right? Because the first time we'll bring it down to our first element. Good. So that's our algorithm, right? Empty tree, negative infinity. Of course, if you're coding this up, you couldn't put negative infinity into here. You'd have to be creative somehow, right? But luckily, I never code, so I don't have to be creative. Right? And the maximum of those is 3 things. All right. Height of the tree. Right? What's the height? How do we compute the height? Everything. We get the height from here, the height from here, and our height is? Biggest 1 plus 1. Exactly. Exactly. The biggest 1 plus 1. Everybody kind of see that? All right, now we get hard again. What's the height of the empty tree? What? We got votes for, I heard a 1 out there, I heard a 0 out there. All right, first off, let's back up. Sometimes you don't know the answer, it's good to back up. What's the height of a single node? Yeah, right, so there's a problem there. What's the height of that tree?
2.
Yeah, it depends on what you count. Right? Different people count different things. Right? So you could count it's a height of 2 because there are 2 nodes. Or you could count a height of 1 because there's 1 edge. And, it's a definition. I don't know, you can, whichever you prefer. All right? So I would say the height is, so now, a single node, what's the height of, I guess we're going all the way down here. The empty tree has 0 nodes in it. How many edges does it have? Negative 1. Negative 1 edges. Now why is that? Well, the height of that guy there, I guess I'm saying, is 0 edges, right? This guy here has 0 edges in 1 node. Everybody agree with that? So my answer is going to be the max of this and this plus 1 to give me 0. So what do I want down here to give me 0? I need negative 1, right? It's kind of awkward, but true. Everybody kind of buy that? So sometimes you have to think about the base cases, right? Sometimes you have to roll back. Oh, I want 0 for this, so what do I want from the empty tree? And to kind of roll back and think about it. Does that make sense? Because nobody's going to really agree that the empty tree has negative 1 edges in it, right? That doesn't really make sense, right? But it's what you need to get the right answer to the 1 level up. All right, so here's the code. You're given a binary tree. If it's the empty tree, I guess here we're counting, returns the height of the tree measured in nodes. Then here we return 0. And here we want the height of the tree measured in edges. Here we return -1. Right? And otherwise the code is the same. It's the maximum of the left plus the right. The maximum of the left and the right and plus 1. Take the max and plus 1. Everybody good? Number of leaves. How many leaves are in this tree? Right? First I have to think about what is a leaf. Is this a leaf? No. Leaf has no children. Right? So we have 1, 2, 3, 4, 5 leaves. Right? How many leaves are in this tree? We ask our left friend, what does she give us? She gives us 3. And this guy, and the right guy gives us 2. And what do we do with them? We add them together. Excellent. Right? We just add them up. Good. What's the base case? We got the empty tree. How many are in the empty tree? Yeah, there's 0 in the empty tree, right? Are we done? All right, so this tree up there, do we got the right answer? Yes.
Actually, I think you're going to cover it. I think you're going to cover it.
Yeah, we're going to cover it right down there. He's on the ball. This guy here, we got the right answer? Yeah. Right? This guy here, do we got the right answer? Yeah. This guy here, do we have the right answer? No. And you can kind of imagine if you start off with zeros and all you do is add, what are you going to end up with? You know, you're going to end up with lots of zero. So that's not the right answer. That's why I put in here, you know, it's good to study these extra weird cases, right? So when we say we're given a tree, we want to count the number of leaves. If it's an empty tree, the answer is 0. If it only contains a single node, if it is a leaf, right? This says that the left subtree is empty and the right subtree is empty, i.e. it is a leaf. Then you count it, right? You get 1, and otherwise it's the sum of what your friends give you. You probably saw this in your last course. You have to be able to traverse trees in different orders and print them out in the different orders. And when I was just entering high school, it's the first time I could at all afford a calculator. You know, before that they were really expensive. And so in the first, and before that, actually I never had one of the ugly calculators. Before that, the calculators all were in a reverse Polish notation. And then when I got my first calculator, they were in normal notation. But let's talk about what reverse Polish notation is. All right, first, prefix. If we want to traverse this tree, we get our one friend to traverse the left subtree and another friend to traverse the right subtree, and we traverse the root, right? And what difference is what order do we do that? So prefix says, I look at the root first, and then I go left, and then I go right. Right? So if this is our tree, and I go up, if I look at the root first, what goes first? It's 5. Right? And then what goes next is we recurse. So our friend then says 3. Right? And his friend says 1, and then they go 2, and then they go 4, and then they go 6. Right? Does that make sense? And here it's plus times 3, 4, 7. Right? People follow that kind of order? And then I think, if I'm not mistaken, reverse Polish notation was this backwards. Right? So in the calculator you would do 3 enter, 4 enter times, and then you go 7 enter plus, which is pre-order backwards. All right. What if you're doing a post fix? You do the left, you do the right, and then you do the root. Right? So I go left, I go left, I go left. There's nothing. Then I go left, I go right. I get the 3. And then I do the plus, then I do the 4, then I do the 1, then I do the 4, then I do the 3, and then I do the 6, then I do the 5. Here you go. Left, left, 3, 4 times 7 plus. Actually, maybe that's reverse Polish notation. Right? Now, everybody kind of following this? It's good for you to be able to trace these out. It's good practice. You should take some trees and make sure you know how to. I have had this on exams. Here's a tree. Give me it in this order. Why do I do that? It's because they're pretty easy marks if you know what you're doing. And it's good to get easy marks sometimes. All right. So in this case, you do the left, then I do the root, and then I do the right. So this is called infix. And this is what we're more familiar with, right? I do the left, left. I do nothing here, and then I do 1, then I do 2. And then I do 3, then I do 4, then I do 5, then I do 6. And here I go 3 times 4 plus 7. Right? Do I say this? No, let me go back and Why is this a useful tree? If I write down 3 times 4 plus 7, that one's already pretty good. But let's write down something else. You know, I guess the order is it's the order of operations, right? We want to do the 4 and the 7 first, and then you want to add on the 3, right? So the trees help you with the order of operations. Everybody kind of buy that? Yeah, everybody good. Right, so in this tree you go 3, and then plus, but then it's kind of in brackets, 4 times 7. All right. If we want to copy a tree, now why we want to, you can't just say T1 equals T2, or you're just copying pointers, right? We want to copy all the data structure underneath. So if it's an empty tree, you just copy the empty tree. Otherwise, you allocate memory for the root, right? I need a new root, and you copy and then you recursively, you copy the information in the root, and then you recurse on the left, you recurse on the right, and you return the pointer to what you've created. People kind of buy that? Deallocating, if the tree is empty, there's nothing to do. But if it's empty, you deallocate the left, deallocate the right, you deallocate the node, right? What happens if I deallocated the root first?
You lose your reference to the left and right.
You lose your left and right tree, and you're in trouble, right? But maybe you guys don't worry about this so much, because if you learned to program in Java, it has garbage collection, right? So with Java, you can just drop things, right? So this was, if you're doing in C, you don't want to have memory leaks. All right, binary trees. Everybody remember what a binary search tree is? For every subtree, everybody in the left subtree of it, for every node, everybody in the left is less or equal to it. Everybody in its right subtree is greater or equal to it. Right? So we're given a binary tree and a key, and we're trying to look for it. And there you go. I just said that. Very good. And before, what we did is we had a loop invariant, right? A loop invariant was our fingers here, which tells us that we have a reduced search space, and the loop invariant says that if it's anywhere, then it's also in this subspace, right? And so then we went one way or the other. But now we could recurse. Oh yeah, so maybe cut the tree in half. We did that. So now, when we're doing it recursively, we can say, all right, what's the precondition? Is we're given a binary tree, and I guess the precondition should have said that this is a binary search tree. All right, it's a binary search tree, and we're trying to find the key, right? So if it's the empty tree, then what's the answer? The answer is clearly it's not in the tree, right? And if the key we're looking for is smaller than the root, then what do? Is we ask the left subtree to find it. And the left subtree either finds it or doesn't find it, right? But we don't even care what the left subtree does. Whatever the left tree does, we return the same answer. Right? The left tree may find it or not find it. I didn't even pause to look. Right? If the key is the root, then I return the data item in that root. Right? And if the key is bigger than the root, then we search in the right tree, and whenever the right tree guy gives us, we return as our answer. Everybody buy that? Remember I said at the beginning of the course that we cover lots of algorithms. You can see why we go through algorithms fast. All right. This one I put in here because it amused me. All right. The next number of the slides are purely for my amusement. All right. Here's a question. The input is a binary tree, and the output is simply a Boolean that says, yes, it's a binary search tree, or no, it's not. All right. So what's the obvious algorithm? If it's an empty tree, is it a binary search tree or not? Right? You clearly read it's yes. But why do I want to say that the empty tree is a binary search tree?
Base case.
Yeah, one, if you say no, then nothing will be. But also, it's kind of like, is it true that every elephant in this room is pink? 5 minutes already. All right. So, is it true that every elephant in this room is pink?
Yes.
Yes. All right. So, it's true that every node in the binary search tree has the correct properties. All right. So, if it's an empty tree, we say yes. And then, what do we need for it to be a binary search tree? Well, the left has to be a binary search tree. The right has to be a binary search tree. The root has to be greater or equal to the maximum in the left and less than or equal to the minimum on the right. Right? Then we say yes. Otherwise, we say no. Everybody buy that? Is this a good recursive program? Why not?
Because if your tree is like 1,000 deep and 2 in, you find it's not a tree, you're still going to go through it.
That might be true. There may be ways of fixing that. What are the other problems here? There's another problem.
Calling your friends too many times? Is that an issue?
Well, okay, that's a good question. Who are my friends? How many friends do I have here? Be careful.
Four. No. Three. Maybe three. 1, 2. Easily 2. Yes, 3. Max.
The people who say 4 failed. What are the requirements of your friend?
They have to be the same program.
They have to be the same program. They have to have the same pre and post condition, right? They have to be smaller, yes, but they also have to be the same program. So how many friends have we got? 2. We only have 2 friends, right? These guys aren't friends. And so what rule am I breaking that I said at the very beginning of this course? Right? What is this guy doing? He's looking in the left subtree. Remember? And I said the rule was the only thing I know about the left subtree is what my left friend gives me. Right? So I break that rule by looking in the left subtree, and I look in the right subtree. Right? So what are the consequences of that? The running time. Well, this is how many friends do I have? Yeah, it's not 4. I have 2 friends. Now, how much work do I do? Well, I don't do a constant amount of work anymore, right? I have to search that left subtree to do the max and to do the min. I have to look at the entire trees to look at the max and the min, right? And so in this case, it's not such a big deal. But if the tree was unbalanced, then it could get it to be n squared, right? So we don't want to do that. We run out. We got a minute left. 0 time. All right. So next class we will finish this example, and I will do my best to painfully go through those tests. And don't lose any sleep. You know, this is what I told what would happen. So life's good, everybody.